That's a challenge. It should be robust against that, but let's see. Hey. Got you. All right, so no more challenges. I love those challenges. Okay, and let's finish with commands. So what is the code for a command? Well, the idea is if we start that code with some stack and some state, well, the code, well, if the command terminates, the code should terminate also at one past the last instruction here with the same stack, but an updated store, okay? And the store being updated as prescribed by the command C. So again, it's going to be a short and sweet recursive function. And let's go over it together. So if the command is skip, do nothing, then we generate no code at all, which is the fastest way of doing nothing. If it's an assignment, ID gets A, then we generate the code that computes A, leaves it on the stack, and then a setVar instruction to assign ID. For a sequence, we just concatenate the codes. Okay, we do the code for C1, followed by the code for C2. Now, for an if-then-else, well, we compile both branches, of course, the if-so and the if-not branch. And then we put them together. Well, we compute the Boolean condition, and we arrange that it skips over the if-so code if the Boolean condition is false. And then the if-so code will, if-so branch will skip over the if-not code. Okay, I have a little picture to explain that better. And likewise for while b do body end, again we are going to test. So skip forward if b is false, otherwise do the body and skip backward to re-execute the test and the body. I don't know, do I have some examples to show you? Yes. And for a whole program, we do the same, but we stick a halt instruction at the end. Okay, so this is a simple assignment. X gets x plus 1. X, 1, add, set x. Easy. Oh, this one I like. It's the prototypical infinite loop. While true, do, skip, end, which gets compiled to just branch backward of 1, which is really branch to myself. Okay, tight loop. And now this is an if-then-else. So if x is 1, then we assign 0 to x, otherwise we don't do anything. So is x equal to 1? If not equal, we skip forward by 3 instructions. So basically we skip here and we stop. Otherwise, push constant 0, set variable x, branch forward by 0 instructions. So that is not nice. That is inefficient. And stop. Okay, so yeah, I promised a little picture to explain the mysterious offsets. Here it is. So basically for an if, okay, so we have here the code for B, the code for the then branch, the code for the else branch. So if B is false, we want to skip over that code and branch to the code for the else branch, which will stop here according to, well, which will finish here according to the contract. However, if B is true, we will continue in sequence with the code for the then branch. And then we need to go from here to there and not execute the code for C2. So we put one of those forward branches. Okay? And likewise for a while. Okay, if the condition is false, then we skip over the whole loop body. Otherwise, we do C and we branch backward. And again, we need to compute carefully the offsets in terms of the number of instructions generated for the various fragments. All right. And as I said, we have a little inefficiency, which we can, which you can actually try to address. So again, can we avoid generating those branch forward 0 instructions when we have an if then else skip, for instance, which is something we often write? So how would you change that compilation function so that it would avoid generating this instruction altogether? There's a hint here. Maybe that function could be useful to you. I don't know. Okay, so we have a nifty compiler, but does it do what we want? In particular, yeah, so basically we have a semantics, operational semantics for the IMP programs that tell us exactly what they should, when they terminate and what they compute. We can even write an interpreter along these lines. I think Benjamin had it in has it in one of his Software Foundation files. But then we can also compile it and run the generated virtual machine code. Okay, and so will we get the same result either way? Are we sure that we are not going to, that the generated code is not going to crash? Okay, and well, that is the compiler verification problem. Basically, we want to make sure that the compiled code does what the source language says. Okay. So let's see, what could we verify? Remember when I described those compilation functions, there were clear intuitions. Like for an expression, the code generated for an expression was supposed to do exactly this. So go from PC to PC plus the size of the code. Push the value of the expression on top of the stack, and leave the state unchanged. And that we can easily claim in Coq. Okay, say, all right, for all expressions A, we have 0, 1, or several transitions in the compiled code from A, from PC 0 and some stack and some state to the length of the code, the value of the expression const with the initial stack and the state. And that's a reasonable claim. However, we are not going to, we need something stronger in order to reason by induction over A. And because for a sub-expression, the start PC is not necessarily 0, okay, and the code compile AX of A is not necessarily at the beginning of the code. It may be somewhere in the middle. So we generalize this a little bit. So first there's the predicate, code seek at C, PC, C prime, and says, okay, we have a big chunk of code C, and at position PC, it contains C prime. Okay, so there's a sublist at position PC, which is exactly C prime. And then now what we can state is the following. So we have a big piece of code C, and at PC, it contains exactly the instructions obtained by compiling A. Then we can do 0, 1, or several transitions from PC, any stack, any state, to PC plus the length of that code, the value of that expression const the stack and the state. And so the proof is a simple induction on the structure of A. And if you look at the base cases, they are quite trivial. So for instance, if A is a constant, here we are just saying the code is just I const of n. And so basically we can go from PC to PC plus 1 by executing this I const of n, which will push n on the stack, and that's exactly the value of A. And same thing for X. And the beauty is in the recursive case. For instance, A is A1 plus A2. Okay. So at PC, we have the code for A1 plus A2, which is the code for A1 plus the code for A2 plus the code for I add. And then we can build the following sequence of transitions. So from that state, at PC, we have the code for A1. So by induction hypothesis on A1, we can go to PC plus size of code A1 and get the value of A1 on top of the stack. And that's a miracle, because at that PC, we have the code for A2. Okay, so again, the induction hypothesis tells us that now we can skip over the end of the code for A2, have the value of A2, then the value of A1, then the stack, and do an I add transition. We advance PC by 1, we leave that value on top of the stack, and that's exactly what we wanted to prove. Okay, and it takes longer to explain like this than to do in Coq. If you look at the Coq proof, it's really short and sweet. Well, you need a few lemmas about this code-seek at predicate, but well, you can find them in the Coq development, and you can even put them in some automation database so that auto and eauto do their work, and that's nice. So, well, that's a really simple proof, and I hope you don't feel offended or insulted in your intelligence by me showing it. I'm spending some time of it because historically it's really important, because that's the first published proof of compiler correctness. That's a paper by McCarthy and Painter, 1967. McCarthy being the famous John McCarthy, who invented Lisp, among other things. And 5 years later only, that proof was mechanized using a proof assistant. So that was 1972. The proof assistant was Stanford LCF. And the authors were Robin Milner and Richard Weirauch. So again, that's the Robin Milner, okay, of ML, LCF, CCS, PyCalculus, and bigraph fame. And it's absolutely fascinating to look at their papers. So that's the introduction of the McCarthy-Painter paper, where they say, well, everything they do, the formalism, the methods of proof, are all intended to serve as prototypes for the more complicated task of proving the correctness of usable compilers. Okay? So back in 67, they already thought about doing it on a larger scale, but stopped at arithmetic expressions. And so this is the Milner and Weirauch paper, which, so I think this was really one of the very first proofs done in LCF. And so they say, well, they would like to do a simple algol-like language with assignment, conditionals, whiles, and compound statements. And the target language is an assembly language for a machine with a push-down store. So that's pretty much what we are doing right now. And we present in full the expression compiling part of the algorithm. More than half of the complete proof has been machine-checked, and we anticipate no difficulty with the remainder. So that might maybe slightly optimistic, but and the appendix of that paper is wonderful as well. So as you see, this is a listing with some kind of old line printer. So the printing technology is 70s. But if you look at, well, these are sequences of tactics that look a little bit like Coq. You have try, you have simple, you have, so I didn't see any intros, but you have apple. Now we write apply. And so, yes? It's not by case. What? No, I mean, what? Well, Coq has some ancestral. Oh, yes, of course. Sure, but still, I find it amusing that even the kind of general look of a proof script, I mean, is as ugly now as it was in 72. Sorry, I shouldn't say that. Okay. So for Boolean expressions, we have a similar claim, although it's a little more complicated. So if at PC we have the compiled code for this Boolean expression, then in 0, 1 or several transitions, we will go from PC to, depending on the Boolean value of the expression and whether it is equal or not to count. So either to the end of the code that we generated or the end plus some offset. Okay? And now we still have an induction on the structure of B, but the case analysis is bigger. So it's good to have a system like Coq to make sure that we didn't forget anything. So let's have a look at those proofs quickly. Okay, so that's the code sec at predicate. So I said we need a few obvious lemmas that relate addition on the PC and concatenation on the code. All right, boring. And again, so yeah, that's the correctness proof for expressions, where you see, well, the various cases I mentioned. Here in the plus case, use of transitivity, induction hypothesis, transitivity, induction hypothesis. and a single add transition. Likewise for the other cases. And so for Boolean expressions, it's a bit harder. There's a subcase whether we branch if it is true or whether we branch if it is if it is false. For each case, we have two subcases. Yeah, for and we even have some sub-cases. And don't ask me. But in the end, all cases are covered. All right, and so now we can finish with commands and prove kind of the expected result. So if your command C started in state st, terminates in state st prime, and you start the machine at a position in the code that has a compiled code for C with any stack and this exact initial state, then you execute all the code of all the generated code, finish with the same stack, and the final state predicted by the operational semantics. So the only difficulty here is that if you try to prove that by induction on the structure of the command, it's going to fail in the while case, okay? Because in the while case, okay, the induction hypothesis tells you something about the execution of the body, but it doesn't tell you anything about the execution of the next iteration of the loop, which is again the whole while expression. It's not any smaller. However, so the trick is to do an induction on this evaluation derivation, okay, which has exactly the right structure. So I don't think I'm going to go into details here. Just a quick check that the proof is not too ugly. No, it's not. So basically, you have one case per evaluation rule in IMP's semantics. So there's a rule for skip, a rule for assignment, a rule for sequence, a rule for if when the condition is true, a rule for if when the condition is false. Whoops. A rule for a while loop when it terminates immediately because the condition is false, and a rule for the while loop where it does at least one iteration. Okay, and now if we put all that together, well, we do get that now if C is your whole program and it executes from state st to state st prime, and you start the machine on the compiled code for this program C in state st, then it terminates without error in state st prime, okay, which is fairly reassuring and shows a number of things. Like, for instance, the machine cannot crash. So we got all these offsets correct in the end. And we didn't forget to push or pop something at any time. Okay, and now a little exercise. So remember this small optimization I proposed to try to avoid generating branch forwards of 0? Well, you could, once you've integrated that optimization in the compiler, you could update the proof of semantic preservation and to show that it to check that it is still valid. And again, you will need a little lemma regarding the execution of this smart branch forward pieces of code. Okay, so yeah, excellent. So what do you think about all that? Is that clear? Have any questions or doubts in your mind about that compiler? Maybe you should. Let's see. All right. So yeah, so that's what we get, and let's see what did we miss, or what could have we missed? So here we know that we compiled correctly. No, sorry. So we know that if the command terminates, then the machine has one good execution, okay, where it goes from st to st prime and stops cleanly. But maybe the machine could have other behaviors, okay, like crash, or non-deterministically, randomly crash or loop, maybe, or terminate on a state other than ST prime. So this concern is not too important because it's easy to see that, to show that the machine is deterministic. Okay, when you start it in one particular state, well, there's only one possible outcome. So if it stops in a state, a given state, it cannot loop, it cannot stop on any other state, and so on. So that's a little bit painful to prove. I don't know if I put that in exercise, but well, you may want to give it a try. But there's a more interesting limitation, which is that if C does not terminate, okay, we have an infinite loop in C, for instance, then we don't know anything about the behavior of the compiled program because, well, the premise of this theorem is simply false, okay? If C is the infinite loop, while true do skip done, then this hypothesis is false for any ST prime. And so we don't know anything about what the generated code is going to do. We hope that it is going to loop, but maybe it will crash, maybe it will stop early, maybe, I don't know. So clearly, so we need, first of all, to make more precise our expectations with respect to a compiler. Okay, in what sense should it preserve the semantics of the source program? And we will also need some richer semantic tools, in particular to reason about non-termination. So yeah, in the remaining time, so let me talk about semantic preservation more abstractly. So let's take a high-level view. There are two programs, P1 and P2, and we want to compare their behaviors. So here, for instance, P2 is a compiled code, compiled virtual machine code that we obtain for P1, which is an imp command, but that's only one example. And let's say we have semantics for P1 and P2 that associate to them observable behaviors. So for instance, for an imp program, what we can observe is whether it terminates or it diverges. And if it terminates, we can observe the final state, for instance. For the virtual machine, we can also observe one third behavior, which is to crashing, going wrong. So let's say we have for each, and then for a given program, we may have more than one observable behavior if the language has some non-determinism inside. Okay. So in general, we have sets of observable behaviors of cardinal at least one. So one if the program is deterministic, greater than one if it has some non-determinism. And yeah, so as I said, for an imp-like language, observable behaviors would be termination on the final state, or divergence, or perhaps going wrong. Although, if I remember correctly, imp's semantics, there's really no way of going wrong because it has only one data type. Or maybe in the terminate state, we don't want to observe all the full final state, but maybe only the values of a few specific variables. So likewise, for a functional language, like simply type lambda calculus or any other pure functional language, in general, you have three behaviors: termination on a final value, or divergence, or maybe going wrong, if or going wrong. But for instance, say you have a language that is imperative and has some input-output primitives, like print. There you will probably need to observe some I/O trace, some trace of input-output operations. Because, for instance, take those two programs, okay? I assign 1 to x and then 2 to x. I can optimize this to assign 2 to x, okay? Because the final state will be the same. And both programs terminate, so they have the same observable behavior in imp. But if I print 1 and then 2, this is obviously not semantically equivalent to printing 2, although both programs terminate and in the same final state. So here, basically, I really want to remember that I outputted 1 and then 2. Here, I only outputted 2, and that trace should be part of what I observe. Okay, and so maybe I want my compiler to preserve exactly all observable behaviors. So the source and transform programs have exactly the same set of observable behaviors. Okay? And that is a strong argument. It's often too strong in practice. So here are a couple of examples. One is that for non-deterministic languages, it is fair game to reduce non-determinism during compilation. And here is an infamous example from C. So in C, the evaluation order of expressions is partially unspecified. So say you have two functions, f and g, that respectively increment and decrement a global variable x and return the current value of that variable. And now you're doing calling f plus call of g. And according to C semantics, actually, you can have two very different results. One is, well, if you evaluate f first, so it increments x, returns 1, then g decrements x, returns 0. So the result is 1 plus 0. But if you start, you can also start by evaluating g, and then g returns minus 1. And then it calls f, which returns 0, and the result is minus 1. And both behaviors are legal according to the C standard. And basically, every compiler is going to choose one or the other behavior. I think you might even be able to evaluate both in parallel, but I don't want to know what happens in that case. Anyway, so some C compilers will give you 1 as a result, another will give you minus 1. But in general, the code that is generated is completely deterministic. So the compiled code has fewer behaviors than the source code. Okay? The source code has 2 behaviors, the compiled code has 1 of them. But that's fair, okay, as long as it is one of the 2 allowed behaviors. Okay? If the compiler evaluates this to 42, something is very wrong. Likewise, I was talking about concurrency. Often, there are many classic optimizations that can reduce the amount of non-determinism present in a concurrent program. So, for instance, here, there's a shared variable x between 2 threads, and x is initially 0. And let's see, what are we doing? At some point, the other thread will put 1 in x, and here we're reading x twice and computing x plus 1 twice and saving the results in local variables a and b. Okay? And so basically, depending on where this assignment falls between those points, you could get a and b 1 as 1, a as 1 and b as 2, if the assignment of x occurred here, or a and b both equal to 2. But then there's a classic optimization called common subexpression elimination, where the compiler notices that you are computing x plus 1 twice. So why not reuse the result of the previous computation? So just say that b equals a, because a already contains x plus 1. And now if you run this in parallel, well, either x is assigned before or after, in which case you get a and b 1, or after, or before, and then you get a and b 2, but the additional behavior a equal 1, b equal 2 has disappeared. Okay? But again, that is probably fair, after all. And so that leads us to what is called backward simulation or refinement. The idea that P2, all possible behaviors of your compiled program P2